And before we discuss the method for the, what they call it, nonlinear method. So what are the definition of nonlinear, right? So nonlinear, all our function, especially for physics, we have all are mostly are nonlinear, right? So linear in this case is just a straight line, but here nonlinear, it can be in various form. So in this, what they call it, in this chapter, our aim is we're going to find the root of a nonlinear equation, right? So although the idea is just similar like the chapter 3, hold on, I have to turn on recording for all of you before I move on more. Okay, so for the, what they call it, nonlinear method, so our idea is to find the root of nonlinear equation. And one thing is, what they call it, you have to remember the optimization also use the same idea, but the difference is optimization is we are going to optimize the, what they call it, the function where it is, although it can be also fx equivalent to 0, either minimum, but for the maximum, it can also not a 0, but it's just the peak of our function or the minimum of our function. But for nonlinear equation, the idea is we are going to really find the root or the solution for the function when the function is equivalent to 0, right? So in this case, usually for nonlinear equation, our solution, our root is being defined what we call as alpha. So alpha is your root, which is equivalent to 0 for whatever equation, nonlinear equation that we want to find, right? So here, for the nonlinear equation, we consider our function is scalar, not vector. If vector, we have what they call it different approach. Vector means that we have what they call it two separate variables, and in this case, we just consider scalar. And another thing we have to consider is our function must be continuous. There is a function which is not continuous, yeah? So if you find that your function is not continuous, the idea of nonlinear equation to find the root cannot be implemented, right? So that is the idea. Okay, so we move on to bisection method, right? So bisection method is a method where we are going to find the root. So for this graph, it's given that if you have a graph, this purple line, the purple line is actually your function fx, and then we are going to bound or constrain our function to a limit or interval, in this case a and b, right? So when we limit our, what they call it, function to a certain interval, so that we can find where is our alpha or our root. Alpha obviously is at f alpha is 0, and from there we can what they call it, slowly slicing the interval so that it will converge into alpha. All right. So condition for a bisection method is the multiplication of these two intervals, fa and fb, must always negative. All right. So when these two negative, then our, what they call it, Newton method will, the bisection method will converge. If it's a positive, it means that it will does not converge, it will diverge, right? Divert from our function. So that's why in here, if you can see that bisection method, we do not require any initial guess, just purely interval, right? So from there, I hope you have read and also listened to the recorded slide. So in this case, when you test this, you have, when you slice this, and it was governed by what we call as a midpoint, how we want to slice the interval, right? So when you have a and b, and after that we are going to, what they call it, get it into half, right? So that it will move towards the alpha, okay? So either A is moving or B is moving, depending how you determine your midpoint, all right? So there is a three possibility in getting the bisection method. But first off, obviously, you have to find your midpoint. And after that, you have to see that this possibility, right? Our first possibility is the multiplication must always be less than 0, which is negative, right? So it means that now your B will be replaced by C, your midpoint. Okay, so in this case, you always test this. Either your A and C will change. It depends on the what they call it condition. Right. So if you multiplication of your FA, your interval the first interval times with your midpoint is equivalent to 0, it means that you reach your solution. Means that the what they call the problem is converged. Your function is converged to the root or to the solution. Okay, and last but not least, if you multiply your FA is FA and FC and then you get a positive, what happened is now your interval is now changed. Instead of AC, it's changed into C and B. So now it will change and it will what do you call it? Move accordingly to whatever midpoint that we have, right? So and then we have the root here must be located within the interval given. Okay. So now let's check our example 4.1. Okay, so example 4.1 is you are given a function and then with a certain interval, you have to constrain your calculation for the certain tolerance. Before we do this, we have to test whether our function have a root or not. Okay, so this is one thing that we have to test. Okay, so let me change my sharing. Okay, so we are going to see that, for example, the first one for bisection method 4.1. Okay, so for example 4.1, so you are given a function, okay, so of fx equivalent to 2 minus exponential x. Okay, so this is your function, right? And then this, since we are going to find the root, is obviously equivalent to 0. Where now we have our interval in A and B is between 0 and 1. And then this calculation, we are going to stop this calculation when your tolerance, which is around 7 times 10 minus 2. Right? So these are the condition you are given how to do this, right? So first of all, if you see the slide, so our solution is, first we have to test if our function, our function has a root. Okay, so how to do this? Right, so to do this is you have to plug in the value of interval into your function. It means that you are given A is 0 and then B is 1. Okay, so when you have this two value, so immediately you test your function. So that's why you have to test your function for 0. Okay, you plug in. So it's just 2 minus exponential 0. You get 1, right? And then you put for 1, which is 2 minus exponential 1. You get minus 0.7183. Okay, so these are how you test the root. So how do you know there is a root in this two function? So what is our condition? Our condition is your f0 and f1 must be less than 0. Okay, so these are our, what they call it, condition. So we check these two. Does it less than 0? Yes, because we have negative for F1. Okay, so you multiply these two, so you get that this is technically less than 0. Okay, so when you check this one, then you start your bisection method. If you obtain these are positive, there is no root in this function. Okay, so if you calculate this thing and then you get both 0, it means that you no need also to do the bisection because there is already the root in the interval. If you are given an interval and then you calculate both you multiply one of these is 0, so no need to perform what we call bisection method too, right? You only perform bisection method when you test it and then you get the value is negative. Okay, so then then we start to calculate our midpoint. Since we are our idea is now you have function like this, right? So this is 0, this is 1. Okay, our function, we imagine something like this, right? So we are going to find where is exactly, I just put it roughly, where is when fx equivalent to 0. Okay, so this is our idea. Now we have, this is A and this is our B. Okay, so we are going to test this until we get our convergence around 7 times 10 minus 2. Okay, so then what we should do is now we have to calculate our midpoint. Right, when you calculate the midpoint, obviously you just get your calculation of 0.1. Okay, so then you get, this is 0.5. Okay, now our interval now is being sliced into half. Okay, so now which is, this is 0 and this is 1. Now is our midpoint is 0.5. Okay, so this is our C, our new midpoint. Then we have to test what is the function of C, which is at 0.5. You put it back again, and then you get, this is 2 minus exponential 0.5. You put again, you get 0.3513. Obviously, this is a positive number. So now we have to what we call double check which pair that we want. Okay, so this is positive. Okay, so our pair just now we test F0 is 1 positive, F1 is minus 0.7183, which is negative. So obviously the pair must with the negative. If you choose F0, it will be positive. You can't do that because why? If 1 and 0.5, it will diverge. It won't converge to F alpha or Fx equivalent to 0. Okay, so now our new pair or our new interval is now, which is 0.5 and 1. Why? Because now FC times with your FB is actually less than 0 because we have 0.3513 and also negative 0.7183 will give you a negative value, right? So you have to do this until you get the convergence. So from there, since we have a new interval, so we have to test the, what they call it, error, uncertainty or error. This is just the average of B minus A. This is you get 0.5. Okay. So after that, when you get the new interval, you have to test for the next midpoint, right? So our second midpoint, now is actually, this is C2, this is C1. Now 0.5 plus this, your half, equivalent to 2. Okay. So from there, you will get what they call it, your new midpoint, which is 0.75. Let me see the slide back again. Okay, so you get this one is 3/4. So you get 3/4, and then you have to test that again, putting the function 3/4. What is the value? All right. So from there, you can test either your what they call it calculation is positive or negative again. Okay. Oops, sorry. So in this case, is actually this you get so how much minus this is 0.170, which is less than 0. So this is negative. So now our what they call it interval is going to change again. Okay, so why is changed again? Because you can see that how they what they call it take care of the interval. Okay, so now since this is negative, so you cannot take 1 anymore because negative and negative become positive. So what happened is now in your this you get 3/4 somewhere here. Okay, so for example, this is not necessarily here. Okay, we're going to see that where is our new result now. Okay, so since it's converged, going slowly convergence, then you are going to test what happened is which pair that we're going to choose now. So we cannot choose one because why? Now we have positive 0.5 and 3/4. Now our new interval is actually 0.5 and also 3/4. Because why? These two will give you some negative value. All right. So from there you can test this thing, and then again you get your what they call it uncertainty. You test back again. So 0.5 minus 3/4, and that you will get around 1/4. Okay. So this value and also this one, you have to calculate until it reach 7, 10 minus 2. Okay, so then you have to, that's why in the slide, you have to calculate until the 4th and 5th midpoint. And then you have to change. What happened is now, if you see in the table, finally, at what point it will converge, right? Sorry. Okay, so you can see that it will converge around, your value is the interval around, let me see, 11 over 6. In the slide, I give you some numeric value, 11/6 and also 3/4. Okay, so your fx is actually in between this value, which is the tolerance is around 7 times 10 minus 2. Okay, so that is how you test the result. So I just show you until C2, but you have to do it, you test it again until you get the condition is fulfill the one that we put it here. All right, so from there, you will know that for the bisection method, no matter what interval you are given, okay, so by considering this two, what they call it, condition, you find the midpoint. And when you calculate the midpoint, your interval must be always negative. And you are going to test your, what they call it, error. And from there, you can see it will converge eventually to the root that you need or you desire. So this is what we call as a, that's why you can see that this bisection method is a global method. Global method means that you give any interval, in the end, it will converge eventually. Okay, so unlike the Newton Raphson method later on, you can see that it does not converge if you give a bad initial value, unlike the bisection method. Bisection method, it doesn't matter. But what are the advantage of bisection method? advantage of bisection method is, for example, you don't know what is the proper X naught. Okay, so when you don't know what the proper X naught initial guess, then you're going to use this bisection if you know what is the interval. Interval we can set to anything. Okay, and anything that you will converge eventually to your root. And the only disadvantage is it going to slow down your calculation. Okay, but nowadays, okay, by hand, obviously you can see there's a lot of step. But if you write computer code, it will eventually converge very fast. This what they call convergence by using the new computer technology and everything. Okay, but this is the idea how you do the bisection method. Any questions so far? Can follow? Okay, so next we are going to see what we call as a Newton-Raphson. Oops, sorry. You might listen to some disturbance in my monitor. So sorry, Kak Yong is still in front here. Okay, the next method that we are going to discuss is a Newton-Raphson method. Okay, so Newton-Raphson method, I already give you how we get the formulation or derivation of this Newton-Raphson method. Oh, it doesn't matter, it's just wording caps locks, right? Okay, so for the Newton-Raphson method, there are two ways how to derive the formulation. One is by using geometric derivation, means that you derive from the line or from the curve of your tangent, and from there you can approximate your X naught or your function. But for the Newton-Raphson method, you require to have initial guess. And if any value that require initial guess, usually is a local method. It means that you have to guess a value that you move closer to the solution. Okay, so from the what they call it geometric point of view, so it's similar like you solve for the what they call least square method. You find the gradient. Actually, sorry, in my recording I forgot to say it's a gradient. So you find the gradient, and from there you can get what is the function of the first order derivative. Right, so when you solve this thing, what happened is when the solution is y equivalent 0, which is equivalent to fx is 0, then the solution, the root is just that your initial guess, where is the starting point minus the what they call it, the gradient of your line. Okay, so if you see what they call it, this formulation, it is same as optimization, but the difference in the ratio or the fraction. Okay, so in this Newton-Raphson for the nonlinear, it require your function divided by the first order derivative. This can be proved by using also some what they call it, analytical derivation. Okay, so from here, when you solve this thing, because we want to make it general as possible, instead we put x naught, we just simplify into xi or si plus 1, because this is a numerical method. Yeah? So numerical method, it means that it must be represented by some changing of iteration. Okay, so or rate of change, what we call it. Right, so for the analytical derivation, the same idea, but we just use some first order Taylor approximation. It means that we only consider fxi and also fx prime, the first order, and the others will fall into what we call it the error of remainder. Okay, so when you solve this Taylor expansion, you can see that we only consider until the first order. So the second order will become your what they call it error, just like in our chapter 1. Okay, so instead of xi, now in for your error is become xi, okay, or chi I. Xi means that this is a point that fall between the what they call it, the first point and also the point that you're going to iterate. Okay, so we're going to see for the example 4.2. Example 4.2 is just the extension same problem used for the bisection method, but now we are using Newton-Raphson method. Okay, so in this case, you are given initial guess, right? So later on, you'll see that in your tutorial, some problem you are not given initial guess, but you have to guess yourself. Okay, that's an interesting numerical experiment, how you want to choose the proper X naught in order for you to converge your function, right? So the same like optimization, you have to identify first what are the formulation that you're going to solve, right? So when you see that for the nonlinear equation, you only have to differentiate once. In optimization, you have to differentiate twice because it depends on f prime and f double prime. Okay, so for this one, it's only the first order, right? So you put back in your what they call it formulation, and from there you can solve the problem. So in the Newton-Raphson method, we have to put condition. Means that this is condition or what we call it the stopping criterion, okay, which is we put as epsilon. Epsilon is user defined, means that we define the what is the accuracy or precision that we want, right? So for example, 10 minus 5. If you want less precision, you can put minus 2 or minus 1. If you have more precise, you can put like minus 10. Minus 10 is, I think, precise enough for the current modern calculation, right? And also, you can also use the second term. Actually, it's just the same, yeah? This one is absolute error, and this is just to get the more precise calculation, right? And then you just tabulate your result, and you can see that at one point, when you try to converge, for example, at iteration 3 and 4, the value become much more, what they call it, converge means that it's going to become same at certain point, it become equilibrium. Okay, so in the end, means that you reach your convergence. Okay, so that's why you say that Newton-Raphson method is a localized method. Means that if you choose your X naught, your initial guess correctly, it will converge. If you choose your X naught very badly, it won't converge. You will forever try to choose to get your what they call it solution, and might be in the end your code will crash eventually because it won't converge, right? So that's why you have to test first what is your X naught, right? So X naught is you also can calculate your error bound. The good thing is how to get the error bound, which is the second part here, and from there you can test this thing. So we just what they call this is your root, your formulation, and then from there you get your truncation error, and you can redefine to equation 4.6, right? So what happened is we're going to check our error bound is either is quadratic convergence, is for in quadratic, right? So you can see that when it's quadratic, you can see at the end, it is just represented by a constant. Okay, so when you test this function, right, for the error, you can see that in the end, the error will become less and less until it become not a number. What happened is because it divide by 0, because it's no longer have any, what we call it, at certain, for example, at iteration 7 and 8, totally we reach our position. So no longer any error because everything is reached to 0. Okay, so that is for Newton-Raphson method. The only addition is might be the error analysis for this one, but you don't have to worry about that so much. You just try to understand and what does it mean. And last but not least is our second method. I hope I'm sharing the correct one. Okay, share. Okay, the second method. Second method is alternative of the Newton Raphson method, if you can see that bisection method, you don't have to put some initial guess. Newton Raphson method, you have to put initial guess. Secant method, you have to put 2 initial guess. Okay, so more work. All right, so for the secant method, it will require for a derivative of a given function f prime. So instead of we use a tangent line, we have to use a secant line, right? So secant lines means that we have 2 lines here. Okay, so you have 2 lines of secant method, and the what they call it, when it's joined at one point, this is where is the solution will fall, right? So when you calculate the secant what they call it method, what you should do is, because we have to start into 2 initial guess, right? So we have a first one here and this second one here, and the straight line is given by your actual function. So when you start for these 2 initial point, you technically will iterate until both of these 2 points will converge into your solution, and from there you can get what is the root for secant method. Okay, secant method is quite popular if you want to have more precision than the Newton Raphson method. Because why? Here, because we need some derivative f prime, but in secant method we don't have to do any what you call differentiation. You just use whatever function that you have, because it use the idea of secant line, and from there you just but the disadvantage is you have to have a 2 initial guess in order for us to solve this what do you call it method, right? So I also provide some algorithm for all these 3 methods, and from there you are going to do some homework later on how to code this thing. Okay, so I already give some brief example. Sorry, how do you get find EI and what is alpha? Did you read the slide? Let me share again. Let me see, does it appear the table? Okay, this one, right? So what is EI and what is alpha? What is definition of alpha? For those who already study or read this slide. Anyone, what is alpha? You can type at the chat. If you don't want to speak, I can read from there. What is the definition of alpha in the first slide in the introduction? Anyone? Are you guys listen to the lecture or no? So what is alpha? Correct. Alpha is the root. What is the value? 0. Okay. So alpha is where your function is actually at alpha is equivalent to 0. Okay. So from here, right. So your solution is your alpha is the root or 0. Okay. So in this case, the alpha might not be exactly 0, but it can be very, very small number, because we do the numerical approximation. Yeah? So when you solve this, what they call it, Newton Raphson method, for example, using this result, okay, you can see our alpha here, technically not really 0, is actually around 0.693. Okay, so this is our root or our solution. You can see that SI and SI plus 1 is the same, meaning that it reached the certain tolerance or the root of our solution. It's approximation. So why we put 0? 0 is when your function is fx is 0. So now you can get what is the value for your alpha. Okay, so alpha can be 0 or not zero according to our solution. Okay, it is going to become zero when you have absolute position. But since this is numerical value, we approximate. Approximate, it means that that's why you have error analysis, right? The error bound. So the error bound, we test, for example, we want position around 10 minus 7. So we test again and it will get certain result. Okay. So what is EI? EI is our error. EI is our, what you call error at our initial guess. Okay, so SI is, for example, when I equivalent to 0 is your initial guess or your X naught. So from there you can have what is our first error. EI plus 1 is when you do the iteration, means that when you solve the what you call it, initial guess, you will get the next point, right? So your next point will accumulate the error. The error will be accumulated when you start the iteration. Remember that we have to find the absolute error, right? So how you get the absolute error for Newton-Raphson? Let us see the, what they call it, the criteria. The criteria is how we want to calculate the error. The error is just the difference between our, what they call, solution for the iteration minus the initial value. Okay, so for example, this is, if you have X naught, this is will be X1. So you get this difference, okay, you get what is your error. Okay, so this is where we put, so now this is our value of your SI here, right, the value, and then this is your alpha. So EI here, instead of we use SI minus SI plus 1 minus SI, we can also can use this kind of formulation to calculate error. Okay, so this is, we are going to find the error bound analysis. It means that we test this thing and then we try to see that either our error bound here fulfill our analysis that we set up earlier. Okay, this one because I choose different example. If we choose same example as this one, you can see that technically your error bound should fall between the one that we set up. Okay, so that's why when we get here, remember this, what they call it, bracket here, straight bracket here, it means that this is absolute value. Okay, so when you have absolute value, you will see that this is your, what they call it, your error. When you use only X naught, you test everything, how it change, and then this is where you iterate it. Okay, so you go to the next point, and then you get what is the value again, and then you can find the ratio. So you find the ratio. This is just the ratio to see either eventually it will goes to 0, because this, if both are, what, if E2 is 0, it will give you not a number. It means that the computer cannot read. Is divided by 0. It's become what they call it, division by 0. So from there, no longer value. So from this one is the, what they call it, the different way how we want to estimate how precise is our calculation. From the table, EI minus alpha, SI is not equal to the value to the table, SI minus alpha. So you have to find what is your alpha first. Okay, so how to get your alpha? You have to do the Newton method first. All right. So if you want to implement this example 4.3, what you should do is you have to find what is your alpha first by using Newton-Raphson method. Okay, then you test all those things. It means that this is an additional step for you to test this what we call function. Okay, so you can do this. Let me correct this one. I think this value. Oops. Yeah, it should be something like this. Okay. Right, sorry, the header is a bit messed up. This one is start from 1, yeah? Okay, so here you have to find your alpha first. Alpha is not exactly 0, eh? So how to get alpha? Do the Newton-Raphson method first, right? So when you have the value of alpha, Okay, then you test what is your, what do you call it, the error. Have you do the interaction method, Nabila? Okay, so this is, you have to do the next step. This is the next step after the interaction. Okay, so give a try and then you can see that how it will solve this thing. All right, so here, let us see the tutorial. Okay, so these are the tutorial that I give to you so that you can test the example that given, and also you can do it next week or maybe this weekend. Or this weekend is Hari Raya. Okay, so you can do it next week when we don't have any lecture. Okay, so from here, you are going to test several functions. I give you 7 questions, all right? So from there, you can test from the what you call bisection method until the second method, right? So from there, from the first what you call tutorial, the first question, you have to do by hand calculation. Hand calculation means that the one that I just show you just now. You do all this calculation, and then now our tolerance. So if you say that find the root of an accuracy, it means that this is the tolerance 0.1 only. Okay, so it means that you don't have to do a lot of iteration. So from there, you calculate this function and you try to converge until it reaches tolerance 0.1. Okay, so after that, you have to write a program to solve equation 1a and 1b by using a larger iteration. Because why? You just enter and then it should iterate quite nicely. By hand, it might be take a very long time for you to calculate until 10 minus 6, but for 0.1, I think it's just maybe 2 or 3 iteration, you will reach that convergence. Okay. Okay, so the third one is you are going to solve the nonlinear equation given by x cos x, right? So in this case, you are going to choose your own initial, what they call it, your interval, not initial, guess an interval. So you have to determine your interval, means that your A and B, okay, by using, first you can test by using calculator, but if you you feel that you can do coding, the code should be same like number 2. Okay, so you can what they call it, solve by using computer code, and from there you can converge. See that either by setting certain what they call it, interval, you can converge this cost. You think what is interval that you can start off for question number 3? If you have cost, right? So the ideal way is you can start into, so remember in what they call it in Python, if you want to this coding, Python is always treated our function in radian, not degree. So when you have to choose radian, so you have to choose your interval also in radian, so that it can solve your bisection method. If not, it won't converge properly by using bisection. You can do it by degree, but you have to, what they call it, change back again later on your, what they call it, your formulation in the function. Okay. So number four is you are going to use interaction method. It should be very simple. So in this case, you are not given also x naught. So you are going to guess your x naught. How to do this? Okay, so I'm going to tell you how to do this. Is first of all, you draw the function. What is the shape of the function? Okay, so when you draw the shape of function, you choose some, what they call, some range of x. Okay, so you can use Excel or Matplotlib, the Python. Okay, so you just plot the function of x3 minus 2. You put, for example, 0 until 10, your x value. Okay, you plot the function, and you see that you identify where is the root by just looking at the function. Okay, so I'm going to train you to be a scientist, how to see the problem or how to solve the problem, right? So how to solve the problem if you are not given some, what they call it, initial guess, because why? This is actually what happened in physics, right? Sometimes we have a function, we solve certain physics function, but we don't know what is the initial guess that we want to test. So the best thing is you plot the function first, see how does it look like, where does the curve, the minimum or maximum fall to. Okay, so and then you try to make it what called cross to the what they call it x and y axis. Okay, so you get this fx equivalent to 0. You see that where it's located. Okay, from there, then you choose the proper x naught for you to solve this thing, right? So for the fifth question, you have to do by hand by using Newton's method. Okay, this is simple. Okay, so you just put your x naught, you solve it by using put the x naught, and after that you change, instead of using 1, you change into 2, 4, 8, and 16. Okay, so when you change your value of x naught, it means that you have to do the separate calculation. So when you test for the different x naught, you see that how much convergence will happen. Is it going to become slower or faster, or it does not converge at all? Okay, so that is the idea of question number 5. Is we want to test either by using different x naught, it will converge or not. Okay, so for the question number 6 is now by using secant method. Okay, so by using the formulation given in the slide, you are going to solve a secant method by hand and then plug in the two initial guess. Okay, so first you test x naught is 0 and 1, and then you reverse the value. When you reverse the value, you see that is it your solution is the same or not. Okay, if same, y. If it's not same, also y. You have to answer that, right? So that's what comment your result. So whenever you see that in the question you say comment your result, it means that you have to observe what is the behavior